Alright, finally the last part of the same lecture. So I will give the first important application of Galois theory to this theory of number rings. And the statement is the following. We know that a prime splits in a number ring, right? So you take a usual prime, it splits into a product of some number of prime ideals. The statement is that whenever this number field is Galois over Q, the Galois group actually permutes the primes transitively. And this has an important application to the formula which relates the degree of the extension to the ramification index and inertial degree. So, here's the theorem. Let me erase this. K Q Galois extension. And then P R, this is P1 P S. So P split into these primes. Galois group permutes P1 PS transitively. What this means is that IE for any I, there is some sigma in the Galois group saying that sigma P1 is Pi. So you can always move this to a given problem. One remark, first of all, what does this mean? Well, this means you take all the elements of this ideal and apply sigma to it. You get some other set of the ring. And it is easy to see that you still get an ideal and you get a prime ideal. So that part I will leave to you, the exercise. So this sigma p, this consists of sigma alpha in p. Okay, so prove, or rather convince yourself, prove that sigma p is an ideal and it is maximal. Assuming p is maximal. So this indeed you get some other prime ideal. The question is why you get one of those and not some other ideal. Well, that's easy to see because when you apply sigma to this equation, right, so then you get sigma PR, but this PR, because P is in Q, P doesn't move, you will be permuting R, but sigma R is just R. So everything in the number ring gets permuted, but that's okay, you still get the same ideal. Right? And then you're applying sigma to these ideals. Well, whatever this sigma I is, and this sigma P1, it still divides P. And these are the primes that divide P. So it has to be one of those ideals. I'm not saying these ideals are necessarily distinct. So there might be ramification indices, so some of them might be the same ideals. But the statement is still true as it stands. Okay, so how do we prove this? suppose Galois group does not permit. Suppose so whatever. Suppose P prime divide P, but the sigma P is not equal to P prime. So these are capital P's for all sigma in the Galois. Now, by the Chinese remainder theorem, there is alpha such that, so this alpha in R such that alpha lies in this ideal, but alpha is congruent to 1 mod sigma P, all sigma. So it does not lie in any of those ideals, whatever they are, but it lies in P prime. So now the norm of alpha, right? The norm of alpha are all the embeddings, is the product of all the embeddings, or rather the images of alpha on the embeddings of K into C. But these are, since K is normal, Galois, these are just the conjugates, the Galois conjugates of alpha. And this element, because it is in P prime, so this belongs to, this is an integer, but since it is also one of them is 1, so this element belongs to P prime. So it belongs to the integers intersected with P prime, which we know is P. Right, so the intersection of a prime ideal over P with Z is this PZ. Right, so this belongs to PZ. On the other hand, this alpha does not belong to sigma P for all sigma, and this implies that it does not belong to P for all sigma, but then you get that this norm, which is now you can take if you run over the inverses of sigma is in Galois group, you still run over all elements of the group, right? So this is the same. So this is the norm, because if you're taking all the elements of the group and you're taking the inverses of all the elements, you still get the same elements. So this element so none of those elements are in P, which, because P is prime, it cannot belong to P. Right? So the product cannot be in P, because P is prime, so this element does not belong to P, so it does not belong to P intersected with Z. but this is again is PZ, which contradicts this statement. That's the proof of this theorem. So here's an important corollary. KQ is Galois. P prime divide this small p. Then E, the ramification index, is the same for both primes, and the inertial degree is the same. Right, what we know, let's suppose this is, let's denote this by E, and this is by F. So we know that N is equal to the sum of EI, Fi. So these elements are now all the same. So the conclusion is that N is equal E times F times S, where this P in R is equal to P1 E P S E. So this ramification index is the same on all the primes. S is the number of primes into which P splits, and the degree of this field extension, or Pi over Fp, is the same. It does not depend on height. That's the corollary of the previous theorem. So how do you prove this? Well, the proof is fairly easy once you know that sigma permutes these elements. You just let me so PR, there are some primes, and then you have this P, E, and then you have P prime, E prime. Yep. And then there are some other primes. So now you apply sigma. Suppose sigma P is P prime. Now there is such a, that there exists sigma such that it moves this prime into P prime. Now apply sigma to everything here. Well, sigma PE, this is equal to sigma PE, of course. And now this is equal to P prime E. So the left hand side didn't change, but the right hand side changed to P prime E. On the other hand, this decomposition is unique, right? The decomposition into prime ideals is unique, which means that this E has to be this E prime. Implies E is equal to E prime. And as for the inertial degree, so you have R mod P. Again, you can apply sigma. Yeah, so this is the quotient ring or quotient field. So you apply sigma. Since it's an automorphism, so you get sigma P So essentially you're taking, so what's the automorphism? Well, the automorphism is apply sigma to elements of R. And what is this? This is alpha modulo P. So you're computing, so instead of computing the coset of alpha with respect to P, you're computing the coset of sigma alpha with respect to sigma P. And this gives you an isomorphism, but this ring, sigma R, is just R. So this is R, and this is P prime. So this means that these fields, this sigma, whatever it was, that moves this prime to this prime, actually induces an isomorphism on the residue fields. Sigma. Alright, so then the inertial degree should be the same. Right, so I'll stop here. We will continue on Tuesday. I will define certain subgroups of the Galois group, the so-called decomposition group, inertia group, and from this we will deduce some important, well, these are tools that are used in number theory to prove some important theorems. We will prove one as a first application. Maybe on Thursday, maybe we will prove quadratic reciprocity using this type of argument. All right.